Assalamualaikum warahmatullahi wabarakatuh. I am Puan Amalina. So we will continue our lesson, chapter number 2, studying compressible flow in pipelines. Okay, the learning outcome is to analyze pipe system consists numerous pipes connected in a complex manner with general entry and withdrawal points by using quantity balance method and head balance method. Okay, basically for pipe system, we have two cases that we are going to solve. The first one is branching of pipes. Okay, where for this branching of pipes, at least we need to have 4 points at least. Okay, here stated as point A, point B, point C, and point D at the center or at the middle. Okay, at least for this case we have 3 reservoir involved. Okay, 3 or more reservoir involved, so the branching of pipes. And second cases is pipe networks. Okay, pipe networks is a new subtopic for degree. Okay, alright, pipe system can be solved by two methods. Okay, analytical method or Hardy-Cross method. Analytical method is via trial and error, whereby for Hardy-Cross method, for cases of branching of pipes, we will use quantity balance method. And to solve for pipe networks, the method name is head balance method. Okay, we go to the 2.5 flow through branching pipes. Okay, for this case, we will use equation to solve the questions. As an introduction, branching pipes consist of one or more pipes that separate into two or more pipes. Basic principles that must be satisfied are, so we will use continuity equation at the junction, at any junction. Okay, so Q1 will equals to Q2, or flow rate towards the junction will equals to flow rate away from the junction. And then B, there can be only one head value at any point. And C, the energy equation must be satisfied for each point. So basically we will use continuity equation and the energy equation. Okay, this is the typical figures to show to us a simple branching pipe system, where here at least we have 3 tanks involved, tank A, tank B, and tank C. So this is under topic of branching of pipes. At least 3 and more pipes involved. Okay, these 3 pipes, pipe A, pipe 1, pipe 2, pipe 1, pipe 2, and pipe 3 is connected at the junction here, and this junction is the point at the junction is point D. Okay, actual direction of flow depends on the tank pressure and elevation. So for this case, branching of pipes, we will not use any pump involved. The water in the pipe will flow via gravity. Okay, and the flow also depends on the diameter, length, and the material used of the pipe. Okay, we will use Darcy-Weisbach equation for FLV squared over 2GD that must be satisfied for each pipe. And continuity equation Q1 equals to Q2 also must be satisfied. Here actually Q in equals to Q out. Okay, for continuity equation, flow into the junction where we know at junction is point D will equals to flow out of the junction. Okay, flow must be out at the highest reservoir and into the lowest reservoir. Therefore, continuity equation can be applied either Q1 equals to Q2 plus Q3. So it depends on how the water flows. So as you can see here, from pipe 1, okay, the water flows from pipe 1, okay, if from pipe 1 the water flows, and then from pipe 2 the water flows and it meet at point D, and then water flows out to reservoir C. Thus we will use this formula, Q1 plus Q2 equals to Q3. But if we assume that if the cases is where Q1 water flows, okay, from reservoir A, and then the water goes to reservoir B and go to reservoir C, right? So for this case we will apply Q1 equals to Q2 plus Q3. So it depends on the questions. So basically, the general problems associated with branching of pipes is to us to find or to determine the flow rate in each pipe. If we have 3 pipes, so we want to find Q1, Q2 and Q3. Okay, example 2.4. This is an example regarding to branching of pipes, and method to solve for Q is by using analytical method. Okay, by using analytical method, right? We have water that flow from reservoir A through a pipe with a diameter D1 100 mm, length L1 150 meter to junction D, from A to junction D, and then from this junction the water flow and leads to reservoir B. Okay, D is at the center, junction at the center, A to D, and then from D to B. And then the third pipe, D3, okay, the water leads from D to reservoir C. Okay, so with that, the water will flow such as that from point A to point D, and then from D to point B, and then from D to C. This is very crucial for us to create the continuity equation after this. So from here you can see that the continuity equation would be Q1, right, equals to Q2 plus Q3. Okay, this is the development of continuity equation. Okay, now we look at the solution of this example. So basically we know that we are going to use energy equation. Okay, so first of all we will apply energy equation between A and B, between reservoir A and reservoir B. For total head losses, we will consider for friction loss pipe 1 and friction loss for pipe 2, since pipe 1 is connected A to D, right, and pipe 2 connected from D to reservoir B. And we know the equation will be as this first equation. Okay, we have pressure at point A will equals to 0, since equals to PATM. Pressure at point B also equals to 0. Velocity at A also equals to 0 because it's very small. VB also is very small. So only left ZA, right? ZA, ZB, HF1 and HF2. So we expand the equation, rearrange the formula, so you will get like this lah. Okay, from the questions we know that given the difference of head between point A and point B, so ZA is 15 meter. If we take as point B as datum, so ZB will equals to 0. So F has been given length 1, diameter 1. Okay, make sure you convert from 100 mm, convert to meter. Okay, and length 2 given 80 meter, D2 75 mm, convert first into meter. Okay, so we simplified the equation until you get this first equation. Okay, since these questions ask us to find discharge for each pipe, Q1, Q2, Q3. So before we can find Q, we need to determine first velocity. So at that point we know that we will have 3 unknown, which is V1, V2 and V3. So if we have 3 unknown, we need to have 3 equations to solve for velocities. Okay, so the first equation we have 2 unknown, so we need to have the second and the third equation. For energy equation, the second one, we will do the energy equation flow from point A to point C. Repeat the same steps as previous. Okay, we will have energy equation. For this equation, we will cancel out PA over rho G and also PC over rho G, since at PC the reservoir is exposing to the atmosphere, so PATM equals to 0. And then same goes to velocity head, okay, because it is very small at reservoir. Same goes to VC. So we are expanding the equation for HF1. So we will have the for FLV squared over 2GD. Okay, but now for point C, we have the third pipe number 3. So we will use HF3. With that, the head losses will be for FL3 B3 squared over 2G D3 squared. Okay. We know that ZA is 25 meter above point C. So ZC, if we put as datum, so ZA will be positive 25 meter. Okay, so substitute into the questions until you get the second equation here. Okay, the third equation will be the continuity equation. So we will apply the continuity equation. Q1 equals to Q2 plus Q3. Expanding equation in terms of AV, and then you expand A in terms of pi d squared over 4. Rearrange the formula, alright, till you get equation number 3. make sure you substitute diameter 1, 2 and 3. Okay, since we have 3 pipe 1, 2 and 3, so you will have 3 unknown, V1, V2, V3. So with that, we need to have 3 equation. Okay, so the last equation is continuity equation. Okay, from equation number 1, we rearrange the formula so that V2 squared is equals to what? V1 squared. And then we simplify the equation. So 15 divided by 3.26, we will get 4.598. 4.587 divided by 3.26, we will get 1.406. So this will become your first equation, the new one. Okay. Same goes to the second equation. We rearrange the formula so that V3 squared will equals to what? V1 squared, and then we simplify. Okay, we simplify the equation, so this one will be your second new equation. Then okay, from the equation number 1 and equation number 2, the new equation, right? Then we substitute into the third equation, so you will get this new equation. Okay, from this new equation, we will use method trial and error. Okay, use your calculator to find for V1. So I have recorded how to use calculator, right? At the next slide. So my answer that I've found is 1.368 meter per second. And then after you have calculated for V1, you calculated for Q1. Q1 is A1 times V1. Okay, and repeat the same steps to find for V2 and V3. Okay, to find for V2, use the previous equation for V2, and also same goes to V3. Okay, right. Alright, now we'll show to you how to use the calculator to solve by method trial and error. Now, alpha x, we will use to substitute V1. So to get x, you must press alpha and x. Okay, then we minus 0.563, third 4.598 minus 1.406 alpha x squared. Okay, and then minus again 0.25. Okay, and then third 8.175 minus 1.5 alpha x squared. Okay, so this will be the equation. Okay, to solve directly this equation, for this calculator, we shall use shift, calculate, and equals to. Okay, then appear the answer 1.368 meter per second. But if your calculator is not as this version calculator, you might use the equation. Right. Try to do this exercise by using the analytical method. So answer has been given. Okay, answer has been given for Q1, Q2 and Q3. And we assume that for this case, the water flow from reservoir A to point D, and then from point D to point B, and from point D to point C. Hope you can solve these questions. Thank you.